very quickly let us go through some standard stuff and then come to the most important question, how well does the least squares method perform in terms of estimating parameters. At the moment we have not asked that, until now we have not asked that question. So, now that you have an optimal estimate, you also want to now predict using this model. The first thing that we always do is, when we want to see how good the model, how good a model we have obtained, we apply the same model onto the same training data set that we have used, or it can be used on a fresh data set. These equations fairly generic. So, given any new phi or the old phi, does not matter, the predictions are simply phi times theta hat. Okay. Now, I have used a hat. Earlier when I was solving the theoretical least squares problem, I did not use a hat. This theta hat is an estimate of the true theta least squares that you would have obtained had you looked at the entire vector y and the entire matrix phi. Okay. So, y hat is simply phi times theta hat, very simple, plug in the estimate, get your prediction. It turns out that you can write this y hat as you see in equation 12, you can write y hat as simply py. P is a matrix purely constructed from the regressors. What this tells us is, in order to construct a prediction of y, I do not need theta, I just need phi, but we had to go through the problem to arrive at the optimal prediction. I do not have to compute theta necessarily, I can directly use the regressors that I used for my estimation. Remember, there is a, that is very important. Here we are assuming that we are using the same training data set. Suppose, let me put it this way, suppose I am given a new set of regressors. Okay. There is a fresh data set that I have obtained, and there is an old data set from where I have estimated theta. So, let us actually abbreviate it, let us call this phi new as phi n and phi old as just simply the phi o. Okay. So, this is the one that I have used for estimating theta, this is the one that perhaps is coming out of a fresh data set. Now, if I want to predict y on this fresh data set that I have, then the first equation that I write is phi n times theta hat. But remember, theta hat is constructed from phi old, which is your training data. It is like you have as an instructor, you have a question bank, you have partitioned them into one for homework and one for exam, other one for exam. So, the phi o comes from your training data set, from your homework data set, and that is what is used in estimating theta. Now, you have to be careful here, where I am just pointing out that the phi that is being written there is being written without the subscript, but you have to be careful. Generally in R, what happens is this theta is stored, so none of this is probably not so relevant. In general, when you fit a model using LM, the object that is being returned stores the coefficients, and then you apply that to a fresh data, it will simply do this calculation for you. But there are these equations which bypass the use of theta. So, you have to be careful when you are using this. At the moment, assume that we are predicting on the training data set itself, so that the subscripts do not matter. What you can see is that y hat and epsilon, y hat is being written as p times y and epsilon is written as p perpendicular y. What is this p perpendicular? It is an orthogonal complement of p. Remember, our least square solution is such that epsilons are orthogonal to the regressors, and you should be able to see that when I take the inner product of epsilon with y hat, I will get 0. So, that is what it is confirming, it is just reaffirming what we already know about the least square solution. So, these equations that you are seeing are being provided for two reasons. One is to compute the predictions given a set of observations, and the other one is of course computing the residuals, and to reaffirm the fact that epsilons are indeed orthogonal to the regressors. That is all. So, this P is called a projection matrix and P perpendicular is simply the orthogonal complement. Anyway, I mean this is just for information. Let us move on. We have talked about pseudo inverse, so I am going to skip. I have also talked about the equivalence of OLS with method of moments, right. Last time in the last class, when we started off with the theoretical least squares problem, we wrote this equation that you see in equation 20, sigma xx, we had used a symbol xx, times theta equals sigma xy. So, from a method of moments perspective, what is the idea in method of moments? You write the theoretical relations between the parameters and the moments and then replace the theoretical moments with time averages. So, if I were to replace here, of course, we are assuming y and psi to be random. If I were to replace sigma psi or xx with its respective estimate, what would be the respective estimate? This portion here. So, this would be sigma psi hat, and likewise the cross covariance with this term. So, this would give me an estimate of the cross covariance. Then you get method of moments, but you see method of moments says you can replace it with any other estimate also. If you replace the theoretical ones with these estimates, then you recover the OLS. So, method of moments and OLS give you the same solution. However, when we talked of OLS solution, we did not have to invoke any randomness. That part you should remember. Whereas, with method of moments, right from step 1, both the regressors and the data are assumed to be random in nature. Okay. So, including a constant term, until now we have not included the intercept, so called intercept term, but it is very easy. All you have to do is you can think of this intercept term as beta, suppose the intercept term is beta, then think of this intercept term as being beta times 1. So, that now you are including 1 in the regressor matrix. So, that is why I have written this equation. If you look at equation 21, what have we done? We have converted the non-zero intercept problem into a ones in the regressors problem. This is a very standard trick that is used in linear regression, where if there is an intercept term, all it does is it includes a 1 in the regressor vector and it says there is a new regressor whose value is 1 and finds the corresponding parameter, that is all. So, an additional parameter is estimated. It turns out interestingly that the optimal estimate of this intercept term is nothing but y bar, which is the sample mean or the simple average, minus the psi transpose theta hat. Okay. So, it is psi bar transpose theta hat, sorry. Psi bar is the sample means of the regressors. Okay. So, it is a very simple solution. When you work out everything, it turns out that the optimal estimate of beta is simply the difference between the sample mean of y and the sample mean of the regressors times theta hat, that is all. So, which means you can afford to decouple this problem. That means you can estimate the intercept term later on. You do not have to estimate it simultaneously with the other parameters. Estimate your theta, calculate the time averages of y and the regressors and use equation 22 to get your beta hat. So, therefore, most of the least squares problems are presented without the intercept term, because you do not have to include that in your least squares formulation. In R, when you use LM, by default it assumes that you are estimating an intercept term. Okay, now we come to the practical aspects of this least squares, where we ask two different questions. for the given model, whatever model I have given, what kind of fit has been obtained. That means how good is the fit for this given model. Whenever, and in fact this is not the question only pertaining to least squares. Any estimation method, any modeling exercise, you should ask two questions. One, how well has the given model explained? Two, is there any scope for improvement? Both are related, but they are different kind of questions. One is telling about the goodness of the fit obtained by the model and the estimation method, and the other is talking about if there is anything, if there is a scope for improvement, if there are further refinements that are necessary. So, here we are asking the first question, how well has the model explained or predicted the given y? And usually you will come across measures like R-square, you must have heard of R-square, or adjusted R-square. We will just briefly talk about that and come to the second question. So, this R-square measure, the famous one that is being presented in all linear regression exercises, is a measure of how much your model has managed to capture the total variation in y. That means y is changing because of some reason, and you believe it is primarily because of the regressors. How well has your model now managed to capture that fluctuation? And you can show first of all, for the least squares, when you use the least squares method to estimate parameters, what it is essentially doing. This is another perspective. We have talked about a few other perspectives before. This is another perspective of least squares. What it is doing essentially is, it is breaking up the sum squares of yk minus y bar. For now, assume that y bar is 0, just for the sake of discussion. Y bar is simply the time average. Then what you have on the left hand side of this equation is simply the squared 2 norm of y. Okay? And what you have on the right hand side, what do you have? The squared 2 norms of y hat and epsilon. So, essentially what it is doing is, it is minimizing this, but what it is doing is, it is breaking up. Assume y bar is 0. So, it is essentially breaking up in this way. It has to be, right, because if you go back to this equation, this is not surprising. Let me write the equation here and show you that this is not a big deal, because we have already seen this before in a different form. What we had said is, find theta such that epsilons are orthogonal to y hat. That is what least squares is doing. So, when I take here inner product, what is the square 2 norm of y? It is essentially the inner product of y vector with itself. So, I have to take inner product of y hat plus epsilon with y hat plus epsilon. And when you do the expansion, you will get this result, using the fact that, what is the fact that we use? So, least squares gives you solution such that epsilon is orthogonal to y hat. So, this breaking up of, you can say sum square wise, or you can say square 2 norm, some people would call it energy, some other would call it variation, whatever you call, this is what is happening by virtue of least squares. Other methods do not necessarily do this. It is based on this expression that the R-square measure is derived. Okay. The R-square measure essentially looks at what fraction of this variation or energy has gone unexplained by this model and by least squares. Remember, least squares is doing it. So, there are two factors playing their roles here in this decomposition. We are doing a signal decomposition, we said earlier, but what we are also doing is a sum square decomposition. Have you seen this kind of a relation before? Okay. Anything else? In Fourier analysis, we have talked about signal decomposition followed by Parseval's relation. But there, of course, in the Parseval's relation, we said completely the sum square in time is preserved by sum square in the frequency. We do not see a decomposition, but you are right, it is a kind of a Pythagoras theorem essentially. If you look at this schematic that we had drawn before, you have y hat which is optimal projection, and then you have epsilon. So, you can see here as well. So, only least squares gives you this kind of a breakup, and R square measure essentially is defined based on this. It is a sum square prediction by sum square total. That means the square 2 norm of y hat by square 2 norm of y. Higher the R square, better is the fit, all right. So, ideally people want R square 1. In fact, getting R square 1 is not possible, because always y will contain something that the regressors cannot explain, which means epsilon is always going to be non-zero. But how much we have missed out is given by R square. And because, see, the other point that you should remember is this R square measure that we are defining can be defined for other estimators as well. I may use MLE, I may use some other method, does not matter. I can always define R square, but only when I use R square with least squares, I can guarantee that R square will be between 0 and 1. Why is that? Correct, because of this property that least squares enjoys. Only least squares guarantees that y hat, the square 2 norm of y hat is less than or equal to the sum square 2 norm of y, and R square is simply a ratio of that, right. So, straight away you can see it is always going to be between 0 and 1. So, if you try to compute R square, which you can for some other method, for the same model, if you use some other method, it is possible that R square can be greater than 1, do not panic, but then that means it is not a good measure to use, all right. Now, but there is a problem with R square. High values of R square indicate good fits, very good, but it does not tell you whether the model is having fits, that is whether the model has been over parameterized. If you have burdened it with too many parameters, then there is an issue. Why I say this? Why do you think R square cannot detect that? What happens if you over parameterize? What becomes very R square? Because you want R square high and high, you want very good fits. So, you keep increasing the number of regressors in your model. Obviously, I mean numerically, as you keep increasing more and more regressors, more and more fits can be obtained, better and better fit can be obtained. That means you will be shrinking epsilon. So, R square is being taken close to 1. What we would be forgetting there is that by including more and more parameters, which will become quite obvious soon, we would be also increasing the error in the estimate of theta. As a result, it becomes unsuitable for use on fresh data sets. Its cross validation abilities will be poorer. It becomes more and more specialized to the data, right. It is like maybe double or triple PhD. Seriously, if you take the PhD, if you ask anything outside the area of specialization, answer would be miserable. BTechs are kind of good least squares fits on the subject, about to be, depends, all right. So, that is a problem with R square, and it is what with that reason that adjusted R square was introduced. Adjusted R square is introduced so as to take into account overfitting, so that the user is being told that there is a penalty for including more and more parameters. How is the definition modified? Now, the definition is modified such that you do not base it on sum square errors and sum square total, you take the average. Now, you calculate the sum square error, not the sum square error, but what is known as mean square error. How is the mean square error calculated? So, if you look at this equation here, we have 1 minus SSE by n minus p in the numerator. Why do we have n minus p? Why is the mean square error? How many terms do we have in sum square error? N, right? Epsilon is an n by 1 component, Ideally, if I were to calculate the mean square error, I should have simply said 1 over n sum square error, but we are calculating mean square error by 1 over n as 1 over n minus p. Why are we doing that? Any idea? So, all that we are doing is in going from R square to adjusted R square, we are replacing this sum square error that we have in equation 24 with mean square error and sum square total by mean square total. When I am calculating sum square total, I have n minus 1 as the divisor, and when I am calculating mean square total, I am using SST by n minus 1, and when I am calculating mean square error, I am using n minus p. Why is that? Remember, your sum square total is actually this term here on the left. In calculating y bar, when I begin I have n observations, but when I calculate y bar I have lost 1 degree of freedom. So, I have effectively n minus 1 degrees of freedom. We have talked about this degrees of freedom before. So, the correct way of calculating mean square total is to divide this by n minus 1. Now, you can also explain why we are using n minus p for calculating mean square error. To begin with, I have n observations and n errors, but before I have computed, before computing those n errors, I have estimated p parameters. So, I have lost p degrees of freedom, and therefore, in calculating mean square error we use n minus p. That is the reason why the mean square error and mean square total are calculated with n minus p and n minus 1 respectively. So, that is how the adjusted R square is. All you can see now is the number of parameters comes into play. As you increase p, what happens to R square? R square is independent of p. R square is in fact getting better as you increase p, but as you increase p, the denominator in the adjusted R square is coming down, as a result of which the adjusted R square, what happens? Decreases, because you have a 1 minus there. So, the adjusted R square gives you some compromise between the fit that you have on the test training data and the performance that you may expect to see on a fresh data. But we have come across another measure, we have talked about another measure that offers this trade off, you recall, Akaike information criterion. AIC also does this, right. So, today people use AIC, but LM, for example, if you want to run LM, if you recall, it reports adjusted R square, it reports many other things, but now hopefully you have an understanding of what it is.